Let me close the door. This is nice. Okay, can I take it? So, I would like to see things like this, okay? I don't know if it's correct or not, but it's nice. Okay? What?
Nothing, it's just
Okay.
nothing.
Time-independent perturbation theory. And we consider a non-degenerate case, okay? Huh? So, what is the problem? The problem is the following. We want to find the eigenvalues and eigenfunction of, did I call it phi yesterday? Okay. So we want to solve this problem, and we don't know how to do it. So we want to find the approximate solution. Huh? But what we know is this, how to solve okay? So what I want to do is, by the knowledge of this phi 0 and a 0, I want to construct an iterative way to compute phi n and en. Okay? So I assume that I can expand both the eigenfunctions and eigenstate in powers of lambda. Okay? So I'm looking for a solution of this type. Okay? Now, keep in mind that you can always write the solution as a power. Okay? However, we should realize that this procedure is particularly effective when I can keep only few terms in this expansion. Okay? So if I have to write down all the terms, then this is totally useless at the end. Huh? So this idea that, and you will see that the more you go in higher power of lambda, the more complex are those terms. Okay? So, as a kind of intuition, we understand that the smaller is lambda, the better is the expansion, or the most effective, or at least we need to keep only few terms. So what does it mean having a small lambda? This we have to quantify in a clear way. So it's not that lambda should be 0.1 or 10 to the minus 2 or 10 to the minus 3. This does not mean anything. So we should understand how lambda will depend on the various parameters of the system in such a way that you can define, say, the perturbative expansion. As you pointed out yesterday, we should expect in general that perturbation is valid as long as the correction that coming from the n terms is small as compared to the previous ones. Okay? So something else which I told you yesterday and I would like to remark again is that there is something really into the non-degenerate perturbation theory is that the nature itself of the eigenvalues, I mean each eigenvalues keeps its individuality, okay? So if you have a spectrum and you can say, okay, this is the nth eigenvalue when lambda is equal to 0, then when lambda is different from 0, this will be modified, will become larger, smaller, whatever. But you can say, okay, this is still the n eigenvalue. So you should not expect that you get crossings. Okay? You remember yesterday I just draw you something like, as a function of lambda, you have E0, E1, E2. Okay? So you should expect that something like this will occur. I don't know, I'm just drawing something like this, okay? So you can say that this is just the first eigenvalue which was associated to this one where lambda was 0, okay? Of course, just imagine the following situation. If you end up in a situation like this, okay? Question. Does this term come from E0 or from E1? You don't know. Okay? So, this situation, and if you get something like this in perturbation theory, means that you did something wrong. Okay? And then you see that in order to get into this situation, that it meant that the perturbation, that correction will become larger than the 0 order. Okay? So, let's go back to what we did yesterday and we discuss it again. So if I plug this thing here, I will get a polynomial in lambda on the right hand side and the polynomial in lambda on the left hand side, the other way around, okay? Then, how do I find the solution? I should put that each term multiplying lambda n, a certain power of lambda, on the left hand side should be equal to the same coefficient to lambda of lambda n on the right hand side. And then I will find an infinite set of equations. Right? The exact solution is an infinite set of equations. Now, what is very good of this set of equations is that you can solve it one by one. So if you solve the 0 order, then you go to the first order, and the first order will depend only on what you find on 0 order. Is this clear or not? This is important because then you proceed step by step. So it's not that you have to solve a big systems of equation. I would like to hear that this is totally clear to you. Not clear, totally clear. Yes, clear or yes, totally clear? Super totally clear. Huh?
Yes.
Enthusiasm. Huh? Okay, so what did I say?
Is there any other situation besides the general case where this breaks down? This formalism?
So time dependent is another case. So now we are doing time independent. Okay? But it's not that it breaks down. In a time dependent, then it does not make sense to talk about eigenstates. You have to find the solution of the wave function as a function of time. Okay? So can you repeat what I said? Since it was super clear. Shout.
Okay. So we start from writing the energy of the solution to this equation as an expansion in terms of lambda, in terms of powers of lambda. And then we plug it back into the equation and then compare coefficients of lambda, coefficients of the powers of lambda, which gives us an infinite number of solutions that we can solve individually for the orders of.
Okay. So, in order to check that you really understood what I said, I would like to ask you the following question. Don't write because it's totally nonsense. Okay? This is nonsense. Okay? Give me the solution. You don't know. Right. So you say no. Just say no.
No.
Now, I would like to ask you, so we don't know if a solution exists, okay? So you have to check if. So let's do it this way. So I just put 2, 1, 0, okay? We still don't know if a solution exists. How do you do it? So for instance, you just write this as a matrix, you invert the matrix and you find the solution. Okay? If the matrix can be inverted. Right? Yeah. Now, the question that I have for you is the following. Is this type of problem have this iterative solution that I mentioned before? That you find first one variable, then the second, then the third, and so forth. No. No. Let's consider another problem. Okay? I just modified here. Okay? Suppose that I have the following system. This. Okay? Now, how do you proceed? You can proceed in the same way, right? You just write the matrix and you invert it, right? But now you see that you can solve it by iteration. Because you solve the first line and you get 2 over 3. Then from here you get y. Then once you know x and y, you get z. So you see that if you have such a structure, you can solve it step by step. You don't need to invert the matrix. Of course you can invert it, it's fine. I mean, but is it clear that in this way you can solve it without getting the inverse of the matrix?
Yes.
Or if you wish, you can get the inverse of the matrix step by step. Do you recognize a similarity between this example and what I said before? If you say yes, then you have to explain me what is the similarity. So you better say no. So, since you said that this was totally clear what I said, then this means, look, you have an equation on your t-shirt which is much more complicated.
You have to explain.
So you have to explain. Okay, so tell me, what is the similarity between this example and what I told you before?
Well, imagine x as the zero. So first we get the original zero, and then y, the second, the first correction. You can solve the next correction in terms of the original,
Right.
and then the second will be the
Right.
first correction.
Correct. So you see, I could have called this x0, and this I call it x1, okay? And this is x2, okay? And then you see that you find x0, which you know. In this case, it would be phi 0 and a0. Once you know this, then you can express x1 in terms of x0. Once you know x0 and x1, you can determine x2 in terms of x1 and x0. And so on and so forth. So, down here, if you want to know x to the power n, this can be expressed only in terms of xn minus 1, minus 2, da da da. So there is no equation here containing x3, or here. Okay? And this is a very important thing, because then you go step by step, and you don't need to solve the whole problem. Okay? Is it clear now? What is So, let's do the first order correction, okay? I wrote it yesterday, so now I write the equation, okay? So, first order, you have something like this. Where is it? No. H0 minus E0 n phi 1 of n plus V minus E1 of n phi 0 of n equals 0. Okay? So this was like the second line with the x0 and x1. Here, however, there is a small complication because something which our unknown quantities are phi 1 and E1. So E1 we don't know. Phi 1 we don't know. So we have to find a way to do it, to find out. So what we do is, first we determine E1. So we just multiply from left with phi 0, n, the same n. Okay? So now you see that this becomes 0 because this is an eigenstate of H0 with eigenvalue is 0n. So here you get z0n minus z0n is 0. Okay? So the only term which remains is phi 0n v phi 0n equal, just put it on the other side, p1n, because phi0n is 1. So in this way we found okay, so can you give me the physical interpretation of this result? What is this quantity?
Matrix element of perturbation.
Eh?
Matrix element of perturbation average on states and many interpretations.
Yes. So yeah. So what is the meaning that there is a shift in an eigenvalue E0n? It's just the perturbation on average.
Yeah.
Okay. So you have certain state with certain wave function. So the unperturbed system is 0n. Now how is the energy of these eigenvalues modified? I just compute the average value of the perturbation on that state. And this will give me a shift. Can we go up or higher or lower? Okay? Now you see that now you determine E1. So once you know E1, then the remaining quantity, which is unknown here, is just phi1 of n. Okay? So the next thing we have to do is to determine phi1 of n. In order to determine phi1 of n, we just multiply this equation by phi0 of m, with m different from n. Now, since we are assuming that the system is non-degenerate, so the spectrum is non-degenerate, then if m is different from n, then the energy Em, E0m will be different from E0m. I'm saying this because we are sure that differences can never be zero in eigenvalues. Okay? So we just multiply by phi0 of n, and what we get? We get H0 phi1 of n minus E0 of n phi0 of m phi1 of n, right? Plus phi0 of m v phi0 of n minus okay? Let's start from here, from this side. This is 0, okay? So, what is the value of this term? Okay? Now I go here. What is the, how can I write this?
EM.
So, EM, E0M, okay?
Yeah.
Times the scalar product of phi0, phi1, minus, so this is the same, okay? This is EM, huh? Minus E0 of n, phi 0 of n, phi 1 of n, plus B okay. Huh? So this I can write as phi 0 of n of m, sorry, phi 1 of n equal this term okay. Now, when I said that now we should not worry about zeros in the denominator, I was referring to here. So this is all well defined. Now, what is this term? The component of the vector phi 1 on the direction phi 0. Okay? So I can write as phi 1 as sum over m different from n of this component times so I don't write. I mean, what I mean is this, I can put it here. Okay.
How, I know it's necessary, but how you got rid of the component in the n direction?
You multiply a bra phi m on both sides and sum all of m not equal to n.
So
Phi m is a complete, phi m0 is a complete set. So
phi of 0 is a complete set, yes, because it's a solution of Schrödinger. I mean, it's an eigenvalue equation.
But how do you know that the correction, the first order corrections do not have a component in the n direction? So you can get rid of that.
So this you can verify by normalization.
By normalization.
I think you can just check. So the only reason why
Sorry, can I? The reason you don't have, so in that equation you can include a term where m equals to n, but according to the lower equation, if m equals to n, then the matrix element of this V is 0. So that term just vanishes.
You mean the numerator?
Roughly speaking, yeah, the top one just goes to 0. It's in a really rude way, but you get the idea.
sorry, I got distracted. Can you repeat?
Is the difference between the m component and the n component it's just that they are a different set of bases?
No, the only thing, no. So for instance, what you can check is the following. So he's suggesting the following. So let's see. I just write here, okay? So, by the way, something something that obviously I just erased, but if you put m equal to n here, you will get exactly what I did before. Okay? So so I think your question is the following. So far I just wrote phi 0, phi n is just phi 0 n plus sum over n different from n of this. Right? Then you say, okay, I should get something, I may get something like 1 plus a, so there is lambda here, okay? And a lambda, okay? Then just verify that, for instance, the state is not normalized. And let me say something about normalization. So, I mean, this is a way you can check that this component is not there. Okay? But, so, something you can try, you just put this on the equation, then you will find that this A should be necessarily 0. Okay? But something else you can notice is that in this expansion, the state phi n should be normalized.
Okay,
So what does it, no, just a moment. What does it mean to be normalized? Now, if I do an approximation, then the state should be normalized at the order in which you are fixing the approximation. Okay? So what I want to say is the following. So phi n should be 1. Phi n should be 1. You know that phi 0 should be 1. Now, of course, I mean, there is something which is weird here. Okay? So if you stop at the second order, if you stop at the third order, it cannot be that each time is always 1. So in order for your calculation to be correct is that if you decide to be here, then the normalization should be 1 plus correction of the order lambda cube. So essentially the idea of perturbation theory is that if you stop at a given level, you can make mistake, errors, an order larger. This is allowed because basically this will not be counted. I mean, you know that you are making this mistake. Now you see that, for instance, if you just stop here, then you immediately see that since this is normalized by definition, in order this to be normalized, this will be orthogonal to phi 0. But otherwise, there is no way in which, okay? And indeed, you find that you just get corrections which only in the orthogonal directions. Okay?
I have a question. So is phi 1 an eigenstate, more or less, of H0, but phi 0 is not? No, the opposite. Phi 0 is an eigenstate of V, but phi 1 is not an eigenstate of
No,
H0.
phi 0. So let me say the following. So the answer is no.
Okay.
So first of all, phi 0 is an eigenstate of H0.
But you put V there and you...
No, just a moment.
Okay.
We agree?
Yes, yes.
Period. Okay, then you have, after I give you two answers, you just ask the third question. Each component, phi 1, phi 2, phi 3, taking alone has no particular meaning. Okay? So if I just, so this I do it here, which is not, so if I just draw something which is clear, totally clear, super clear, where are we? Here. Okay, so I repeat. Phi 1 is this piece. Okay? What is the meaning of this? This is just a correction to the wave function, but it's not a wave function.
Can I put my question in other words?
No, first you tell me if the answer was okay. Then you put the question. No. Okay. So I asked you, what is the meaning of phi 1? Does phi 1 for you as a meaning? But let's not talk about phi 1. I just take this in this expansion, 5 to the 23 of n. The 23rd order in perturbation theory. What is the meaning of phi 23 of n? Yes, but is there a meaning of a wave function? No. So the wave function is the whole thing, that you stop at some order. But if you take the single pieces, these are not wave functions. Now you are allowed to ask a third question.
Yes, then I have two questions instead of one.
Okay.
What if I want to have a wave function of the system after its perturbation? Can I have that or?
Yes, and this is this. Or this. You tell me, okay, I want to stop at the second order, and this is the sum of these three pieces. But this is the sum that has the meaning of a quantum state. Not each single piece.
Okay, but still the previous question.
What was the previous question?
What's the difference if I put phi 0 and then h naught and then phi 1?
I did not
This gives me 0 because we just did something like this.
No, I did not understand. Can you write on the blackboard? I did not get.
We just did something like 0, h naught, phi 1. And it got us 0. But at the same time, we can do this.
This is not 0. Can I?
Yes.
No, this is equal to E0. So I just put M and N, I don't know.
No, this was n. It's the same n.
N.
Yes.
Okay, this is N. And then I have phi 0. Ah, yes, if this is N, this is 0. But I just found that there are no correction along N of phi 1. So can I make a completely different example?
There is just a S naught in between phi 0 and 1.
Okay, can I ask you a question? So I have a vector. Okay? I have a vector of length unity. Okay? I apply a tilted magnetic field a little bit, and I ask you, what is the correction such that the new vector has the same length unity, but it is aligned to the magnetic field? The only possibility to have a vector which is in a new direction with the same length is that the correction is only orthogonal to the initial direction. Because if you get the correction which is here, then you will get something which is longer. So okay?
Yes.
Do you want another explanation just to confuse you?
What's the length here? What's the length?
The normalization.
Okay.
Okay, are you ready to get confused? Because now it's super clear. No? Nadine, where are we? There. Oh, now I should learn two new names.
Ezroy. Ezroy.
Ezroy?
Ezron.
Eh?
Ezron.
Ezron, okay. So we are Michael, Edward, Nadine, Amel, Ezron, Putri. Ah, you told me, sorry. Putri. Ezron? Okay. I try with the last one.
Omar.
Omar?
Mariano.
Oh, Mariano is symbol for me. Okay.
You should try his name. He's very easy.
Yeah. I was waiting for
Jesus.
That's also symbol. Where do you come from?
Costa Rica.
It's a recording.
It's a recording. Can I give you another explanation? Okay? So this is more confusing, but it's good so that you continue thinking or start thinking before. Okay? So, what is the effect of perturbation? Now, suppose I have a given state, okay? So, the effect of perturbation is twofold at the first order, okay? So, first, the only thing which happens is that I can forget about how the wave function is modified. And I just say, look, so for instance, let me say the following. So this is harmonic potential, okay? So we know the solution, okay? The ground state solution, the wave function will be something like this. Okay? Now I want to consider a situation in which here the potential is slightly modified. It will be like this. Huh? Then in the first order, the perturbation has two effects. One effect is related to the fact that the energy changes. Okay? So if you take this particle, I mean, it has some probability to stay here, but when it stays here, the potential is slightly lowered. Okay? So the eigenvalues will change. So the energy will not be h bar omega over 2, but it will be h bar omega over 2 minus lambda something, which is the fact that, you know, here the energy is non-zero, but it's not zero, but it's something else. And this is contained in the fact that you determine E1 just as the average energy computed on the unperturbed state. Then the next effect is to determine how the wave function is modified. In order to determine how the wave function is modified, then what I need to do is to determine I just use a given basis. Now, the unperturbed states form a basis. So, in terms of this old basis, the unperturbed basis, the new potential will induce transitions. I will have matrix element which connects the ground state to all the other states. In principle, to all the other states. Then the effect may be small, large, it does not matter. So this means that the new wave function will be given by a superposition in all the other basis set, in all the rest of the sets, okay? And this is contained here. So basically I will have components not only in the ground state, so just say m equals 0, but I will have components which are in all the other states. And the smaller is the perturbation, the smaller are those components. Okay? So at the level of energy, if I look at the first order, I just have just a shift. Okay, so this is what I want to say. Huh? Is this bit clear or not? Nadine is my thermometer, so I should decide today. Tell me, was this clear or not? Okay, well, from where it was not clear? From the beginning of the course? No, from the beginning of this lecture. No, so from where? So just ask me question. If you don't ask me question, I don't know what to say. So I know what I say, I will say, but I really would like to understand what is not clear.
Is what you are telling us is that phi 1 is related to the second energy level?
To any. Let me see if I can find Okay, so I have another example which is beautiful. Don't write because there is nothing to write. Nadine?
Yeah.
Are you with me? Do you know about, seriously, I'm not joking. If you don't, I mean, I'm just teasing you, I would like to tease everybody, okay? So if I will tease also. Can you repeat the name?
Ezroy.
Ezron. Okay. If you wish, I can tease Ezron, if you prefer. Huh? Or if you have any other preference, you tell me and then. Okay. So you know waves. Okay. So let's consider. So you know electromagnetic waves. So suppose that I have a cavity, a piece of metal, whatever, just a cavity, with some dielectric constant. So you know that in the system there can be, so if you have boundary conditions, then you can have certain standing waves. So let's do another example. So let's take a guitar. Okay? Do you agree that when you play, basically you have certain modes that, right? Because, okay? Is this clear?
Yes.
So let's consider one particular mode. Okay? I'm not able to tell you why. So one particular mode which will correspond to certain wavelength. Okay? Now, my question is, let's consider this as just the zero order. To this mode, there will be some energy associated with it. Okay, because there is some kinetic energy, whatever, depending if you throw there will be also some potential energy, but there will be some energy. And depending on the type of mode that you are considering, then you can say, if you forget about dissipation, damping, right? There is some energy associated with it. Okay?
Yes.
Now, and you know that, suppose that you know everything, okay? You are the world expert in guitar strings. So you know that if the string has a certain thickness, the section is spherical, and you use gold, I don't know what is the material, which has a certain density, you can determine everything, okay? Whatever you want to know, you determine. Now you suppose the following, that even though you are the world expert in guitars, in strings, you made a small mistake such that the string is non-uniform, but say in a certain region, I don't know, just saying where, it will be thicker. So the section is not 1 millimeter, but it's 1.1. Okay? Huh? Now, and other properties. I don't know, I'm just thinking, inventing, so I'm not sure that, or it's a different material in some parts. Okay. So, is the wavelength, so is the, let's do it this way. It's not uniform, but just in the central part it changes a bit. Now, the sounds probably will change. This means that the normal mode will be different from the ideal case. So, I would like to ask you two questions. Since somebody wants to buy your guitar, then you have to understand what changed in this string. Okay? you want to ask yourself are, and this is just because I did to ask those two questions. So first, what is the energy of the new string? Is the question well defined or not? It's a well defined. So probably because, you know, there's also this standing wave, but if in some part it's thicker or it's thinner, this will change. Okay? And then the second question that you really would like to know is if the oscillation is just a single harmonic, as it was when you had the ideal situation, or not. Okay? Now, let's try first to answer the first question. Is the energy modified or not?
Yes.
In general, it will be modified. Okay? And if you want to determine what is the change, then what I'm telling you is that, look, in first approximation, essentially you take the old solution of the string and you just compute the average energy using this as an approximation. But now the mass is not constant, but we'll have a bump. Okay? And this you will get a correction just by considering the old solution, but with a new configuration, with a mass change or thickness change or whatever density change. Huh?
Yes.
It's a good approximation. And this is what corresponds in determining E1. Okay? The second question I would like to ask you is that, is the oscillator mode the same as before? Now, since there is a perturbation, local perturbation, most probably if it was just a sine of a certain length, wavelength, then if there is a perturbation, a sine function is not a good solution. Okay? So probably it will be, you know, a sine function, let's consider a simple situation, a sine function or quasi-sine function, whatever, such that, however, the wavelength changes in the middle and becomes similar to what was before, far from the perturbation. Huh? Now, question, how can you write down some wave using, in which describe this? It's not enough to consider one sine function. Probably you have to take several sine functions. So you do Fourier transform. Okay? So what are you doing? You're just using a basis set of Fourier terms, and you can construct some superposition of Fourier terms, which will give you this new solution. So you are using the old solution, which was sine with different harmonics, so sine, cosine, whatever, with different harmonics, and then you write down the new solution in terms of the old basis set. Here. Okay? So these are the harmonics. Okay? These are not harmonics, okay? But the idea is similar. You're just using, basically, you're starting from a problem that you know, and this is a good solution. So, but in order to construct the new, the new one, then you have to get superposition. If you have a string with a bump or with something, you will not have a perfect harmonic with a different length, wavelength. You just get something else. And in order to get this something else, you can reproduce it by superposition of different periodic harmonic, different harmonics. And the logic is similar here. Is this better or not?
It's better.
This is super clear and you are a liar or you're saying the truth? Huh? No, really, I'm joking. Is this okay? Is it better?
Yeah.
Okay. Now, you can do the third term. Sorry, the second order correction. Now, again, it's much more complicated, and the corrections are awful in general for the wave function. But for the eigenvalue, it is simple, more or less. And you will get something like this. I just write you the solution. The procedure is the same. Just take the second equation, substitute what you got before, then you multiply by phi 0 of n, and then you will find 0 a2 of n. Okay? So if you do this, then you will find this symbol result. But then you have to put what is phi 1, which we wrote before. Okay? Okay, I just try it this way. Now, as I said before, E2n has no meaning by itself. The meaning is given by the sum of the E0, E1, E2, which tells you what is the just notice that if n is the lowest eigenstate, so it's the ground state, this is always positive, and this is always negative, because all the energy difference will be negative. So the second order corrections to the ground state are always lower the energy. So the first order can be both signs, because you have to average the perturbation on the ground on the ground state, and depending on the perturbation, this can be positive or negative. But the second order correction will be always negative. Okay? Shall we do an example? Yes. Now, did you study for the harmonic oscillator, the distraction and creation operators? So you know this. Okay, so I would like to consider an harmonic oscillator. So H0 is harmonic.
No
just a moment. I would like to. Where? Plus 1/2. Yeah. So, but it's not really important. I mean, it will be a constant, so it's shifted. Yes. Okay. Then lambda v is minus lambda h bar omega x over L cube.
L is a length.
S is the length, okay?
Length of what?
So when you write the harmonic oscillator, then you can write dimensionless. X over L is dimensionless, and then you can write X over L as A plus A dagger. So you construct the L by the H bar, omega n, whatever, okay? Now, no, I would like to check what we are going to do. Yes. Okay. So, how do you write x? X over L.
1 over square root of 2a plus a dagger.
Okay, good. So the so you see, if you have a quadratic plus cubic, how it will be the potential? So it will be something that starts like this. So when x is very small, it looks almost quadratic, then it will become much higher on one side, and then it will turn into minus on the other side. So the first question I would like to ask is, I would like to determine the correction to the eigenvalues. Okay? So let's consider the lowest eigenvalue. Should we run? I think that there was some fire alarm or something. I think it was some, no?
Run through the right.
Did we get a minute of the about parallels?
I think it was a short.
It sounds like a trap.
Oh.
Going backwards.
Yeah.
You're getting ostracized.
Okay. So tell me. So the ground state energy is something. Good. So the first thing we would like to determine is the first order correction. Okay? To the ground state. Tell me, what should I do?
Matrix element of lambda v.
So I have to compute the ground state is 0. Okay? So I just use an n. So it's 0. Lambda v. So this is T1. 0. Huh? Lambda v 0. What is the result?
Expand the
It has to be 0.
Why?
Because if we cube up the x operator, we will have either. We'll just get non-diagonal, non-orthogonal.
Right. So this is 0. Very good. Now, if I look at the wave function, okay, what is the wave function in the ground for the harmonic oscillator?
Gaussian.
It's a Gaussian. So it's something which is even if you change x in minus x. Okay? Now the same thing that why we get 0, you can see in this way. So x cubed is odd, it's an odd function. So basically you are just rising a little bit the energy on one side and lowering on the other side. In a perfectly balanced situation. Okay? So say on this side, okay, on my left side the energy is lowered, on the right side it increases, but exactly in the same way. So on average there is no increase. Okay? So we should go to the second order, right? Now, since you are very fast, this you do it as an exercise. Okay? So basically you have terms like this, right? E0, 0, minus E0, M, okay? Then you have 0, V, M, modulus squared. And then you have to sum, okay? Now, one question. How many M you have to consider? Huh? Are you not here? What did you say?
No, I would say that not many, because
Okay, not many. How many?
like it goes to the energy goes like a square, like decreases.
Just look, use the same argument as before. So you just found out that by just counting the number of A and A dagger, you understood that the diagonal term is 0.
Has
Okay?
to be 3 or something.
So basically, if you take the power cube, at most you have, since you are starting from 0, so at most you can reach 3, m equal 3. So you will get, if you expand, if you put this there, you will get A dagger 3, then you will get something like A dagger cube and things like that. Okay? But the largest M in the ladder is when you just sandwich A dagger cube. Okay? So if you put M equal 4, then you get 0 because there is no A dagger 4 to connect those states.
Yes.
Okay? So this type of analysis, now in this case you would have found it immediately, but this type of analysis is important so that you understand what you have to do. Otherwise you risk to compute many things which are 0. Okay? Once you compute the matrix elements, you know the roots, then you divide by the difference in eigenvalues, and then you will find the result. So this you do it. Okay?
Same thing, we're going to scan it and send it to you.
Yes. So, let's do the following. Today or tomorrow, you send me the first 2 exercises. Okay? Then on Thursday, I will give you some more. And then you send me a second bunch, otherwise I get confused. So, something which... so when you send me the 2 exercises, please separate. So I am a dumb person. So you just say, this is exercise 1 and this is exercise 2, so that I understand that they are separate. Okay? And just put also the text, because by now I completely forgot what was the text of the exercise. Okay? So you just write what I suggest, and then